All right, last lesson. 4.4 is the dot product. So the dot product is continuation on what we were talking about yesterday with the vectors. All right. So we could add vectors together. We could subtract vectors, and what you had was a resultant vector. All right. We talked about that. That gave you a new vector. You basically took one, tacked it onto the end, essentially. All right. Now, by contrast, the dot product of two vectors results in a scalar or a real number rather than a vector. Remember yesterday when we were talking about the combining the forces together? All right, we had the things going in two different directions, and you had the resultant force. Remember doing that? At the end of the day, Taylor was up here. We were showing if we push in different directions, we had the resultant force. Essentially, that's what this is talking about. How much is put together at the end of it. This becomes your scalar. All right, so definition of the dot product. So dot product says you have vector v and vector w. The dot product v dot w is defined as follows. Multiply your I terms together, multiply your b terms together. All right, and it's going to be the sum of the products of their horizontal and their vertical components. So this is a pretty simple concept. If I have v times w, I have my v and w right there above. All I have to do is take my I terms, multiply my v terms, or my j terms, and multiply them. So my v term, 5 is my I term there, and -3 plus -2 times 4. Okay, 5 and -3, -2 and 4. Just be careful with the negative signs and the subtractions. So like in v there, we have -2j. Make sure that you make that a -2 here. Same thing with the w, that -3 has to come along as well. So what's 5 times -3? -15. What's -2 and -4? Or -2 and +4? -8. -15, -8 is -23. Done. I got dyslexic there. Okay? You guys do VV. V dot V. All right, so what's V dot V? What'd you get? I got 29. Brisket. All right, here we go. So V, 5 times 5, right? That's from right here. My I term. V and V, it's the same one. All right, plus my J term. -2, -2. You only use one. You only have one vector. Okay? Yeah, but it's both the same one. Okay? So what's 5 times 5? You're acting like Samson now. All right, what's -2 times -2? 4. 29. You like my answer better now? You just multiply it by itself. That's it.
No, it still doesn't make sense though.
It doesn't make sense. Multiply V times V. V dot V. It's the only one you need. Multiply your I terms, multiply your J terms. Well, look up here. V, W. That's two different vectors. We just use the same vector. All right. So that one's pretty simple, I think. Multiply your I terms, multiply your J terms, move on with life. All right? Now, Next one. Here's where it becomes a little bit better, a little bit more along the lines of what we've been doing. Okay? So when you're finding the angle between two vectors. So again, we have an alternate formula for the dot product. You can use that. But we're going to focus mainly on the second one for the formula for the dot product. So if V and W are two non-zero vectors, and theta is the smallest non-negative angle between V and W, then we have that. The cosine is equal to V dot W over the magnitude of V times the magnitude of W, or it's also the inverse cosine of V dot W over the two magnitudes. All right, let's look at an example with that. We'll do it visually as well. All right, so let's start. I'm going to graph those two vectors. All right, if I'm going to graph these two, let's go with V first. So 3I plus 2J. Remember, we have our horizontal component and our vertical component. So for V, I'm going to go 3 to the right and down 2. All right, that's where my terminal point's going to be. That would be this vector right here. That would be V. Okay, now if I want to graph vector W, where do I need to go to for my terminal point there? -1, so left 1, and then where? And up 4. -1, 4, right there. And that would be vector W. Now, take a notice here too, it says that this is the smallest non-negative angle, correct? So when I look at this one, this is the angle I'm talking about here, because this is smaller than this. See what I mean? All right, I'm going to find this one. If I wanted to find this one, I just subtract it from 360, okay? But the smallest way between those two is this angle right here. So that's the angle I'm going to be looking for. Right here, call that theta. All right, so I am going to use the first formula, the one that's just cosine dot product over the magnitudes. All right, so I'm going to write this one whole way out. So I'm going to have the cosine of theta is equal to the dot product of 3i minus 2j and I negative I plus 4j over the magnitude. Remember the magnitude out to square root both of them. This is from yesterday's lesson. Square root of, this is V, so I have 3 squared plus -2 squared times the square root of the magnitude of W, which would be -1 squared plus 4 squared. Okay, again, remember the magnitude is essentially the length of it. All right. Yep. The two magnitudes on the bottom. Correct. All right, so on top, when we do dot product, the i's and j's go away, right? So on top, I'm going to have 3 and -1, which is my i's, plus my j's, which is going to be -2 and 4. All right with that? On the bottom, I have the square root, so 3 squared is 9, plus 4 squared is 13. I have the square root of 13 and the square root of 1 squared, 4 squared, so 16 and 1 is 17. Right, and that's what cosine of theta is still equal to. And then simplify a little bit on top, I got -3 and -8, so it looks like -11. On the bottom, I multiply that, 221. All right with that? All right, so now I have it down to one single number. I can punch that thing into a calculator. Now I have the cosine of theta, so now I have to do the inverse. The theta is going to be the inverse cosine then of -11 over root 221. All right, punch that in the calculator. Everybody got one? All right, good answer of 137.7 degrees. And then all I did was just punch that in a calculator. So the angle between those two vectors up there is going to be 137.7 degrees. Go on. You want to?
Yeah.
Can you catch?
No.
Wilson, I'm going to throw it to you.
Fish ponds, there's nothing but their cornhole.
What?
Their cornhole.
I'm pretty good.
Yeah.
No. You can tell by the way it corrodes.
All right. Questions on that?
Exactly.
Anybody? So that was the angle between those two vectors.
I wanted to take you to learn the spin on cornhole throws.
So next one we have is parallel and orthogonal vectors. All right. So two vectors are parallel when angle theta between the vectors is 0, between the vectors is 0 or 180. Can't speak. And two vectors are orthogonal when the angle between the vectors is 90. So that's basically perpendicular. Okay? The two angles, if I have two vectors, those are parallel and those are parallel. You all right with that? And that would be because the angle here would be 0 on the first pair. This angle would be 180. All right with that? Second one, it would have to be at 90 degrees. So this would be orthogonal, essentially perpendicular. Okay? It could be in any way too, like that. All right? So those guys would be orthogonal. All right. So dot product and orthogonal vectors. Two non-zero vectors v and w are orthogonal if and only if their dot product is 0. So if you do the dot product, you get 0. That means that they would have, it would be 90 degrees of difference between the two of them. Okay? So the way to check those, you just do the dot product. So looking at this guy, I have the vectors b is 6i minus 3j, and w is I plus 2j. We want to know if they're orthogonal. Do the dot product. So v dot w equals. Finish it. Tell me what you get. Just apply the dot product.
Snoop was looking for someone earlier. Yeah, he's a happy person.
All right. So dot product. What'd you get? 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 All right. So we took v. V is going to be 6. I is 1. Plus, we have negative 3 times 2, right? Multiply your i's, multiply your j's. 6 minus 6, which is 0. So are they orthogonal? Yes, they are. I can't spell. I tell you, I remember the first time I learned this, I'm like, why the heck do we not just say perpendicular? You know what I mean? Now, I think the biggest reason why we won't ever hit that, when I took the class in college, it was called linear or something. I think it's because after a certain point you get into three-dimensional stuff. Okay? So on a plane, I have perpendicular, right? Now when you come into 3D, it's really perpendicular, but so is this. So is this. So is this. You know what I mean? So because it's 360-degree rotation and still be in that right angle, that's orthogonal. Perpendicular is only the one certain way on a flat plane. Pretty sure that's why. Still, I'm not sure why we didn't have to say just perpendicular. But questions on that one? I think that's pretty easy. Now, here's where we get a little bit tougher, just a little bit. All right. So a vector projection of u onto v. So if u and v are two non-zero vectors, the vector projection of u onto w. Why do I have? Is this formula here. All right. So it's the dot product over the magnitude squared times the vector. Now, what this is essentially doing is, I'm going to try to draw a little thing here. Say this is, this would be v, and this would be u. The projection of, if those are my two vectors, the projection of u onto v would be essentially doing this at a right angle. Okay? It's basically flipping it and setting it at a right angle. So it's not always going to be 100% straight, but it's projecting it to a right angle. To a right angle. To a right. To a right angle, okay? That's what it says. To a right angle. I need more like the verbal thing. Better? All right.
That's the angle, that's right angle, I see.
This angle. Okay? All right. Holy crap. All right, so the projection. I want the projection of V. What the heck? What is going on? What is that?
No, your pen is pressure sensitive, so the harder you push down.
You might just see the ungluing of Mr. Thomas today. It might happen. What is Okay, projection of V onto U. Projection of, well, actually it's U onto V. This is U, that's V. Don't correct me. So, I have the dot product of U and V over the magnitude of V squared times vector V.
What does it say on the left?
PROG. Projection sub V big U. It says exactly this. Okay? Alright, so start plugging stuff in. So on top, I'm doing the dot product. So the dot product is going to be 2 times negative 2 plus 4 times 6. Pretty simple there, right? The bottom, I got to find the magnitude of V. So, I'm going to have V is negative 2 squared plus 6 squared, and then the whole thing squared. And then I still have W hanging out. I don't like to bring W back into the very last step. Okay? V. I can't read my own writing on my notes. V. All right? We'll bring it back in. That's how to get it back into the letters, to bring I and J back. All right, so on top, I have -4 plus 24. On the bottom, it's going to be the square root of 40 squared times V. Okay? So -4 over. So this is going to be 20 on top. On the bottom, that's just going to be 40 because these guys cancel each other out. I still have times V. So this is what, 1/2? Agreed? Now I'm bringing V back in, and 1/2 is just my scalar. Okay, so I have to take 1/2 times V. V was -2I plus 6J. Multiply, just distribute that 1/2 through. So I get -1I plus 3J. And that would be my projection for my projection vector. Can't think of the word.
You write that as -5.
You could write it as -I or -1I, either one. Both means exactly the same thing. All right? So that would be how you find the projection of one vector onto another. All right, home stretch. Home stretch. We got 2 problems left. 2 formulas, 2 problems.
I enjoy these. I don't know why. So if it was projecting V onto U, then would U be below? No.
Yes. Yep.
Nice.
All right. Here we go. Vector components of V. So, components are basically, I'm trying to think of the easiest way to do this. Well, we're going to do something called decomposition. Okay? Decomposition of a vector. So what we just did there with the projection, we took 2 of them, we found that third, right? That was our projection. Basically, this is how you undo that if you're given the projection and you want to work backwards. Essentially, that's what that is. All right, find the 2 original vectors. All right, so vector components of V. The V and W are 2 non-zero vectors. Vector V can be expressed as the sum of 2 orthogonal vectors V and V2, where V1 is parallel to W and V2 is orthogonal to W. All right, so thus V is V1 plus V2. The vectors V1 and V2 are called the vector components. Process of expressing that is called the decomposition of V onto V1. Sounds really confusing, doesn't it? Let's do the example. All right, so let U equal 2I plus 4J, and V is -2I plus 6J. We want to decompose U into 2 vectors, U1 and U2, where U1 is parallel to V and U2 is orthogonal to W. All right? So, the first one we just... All right, so V1 is easy because V1 is just the projection of it. And we actually just did that, right? If we bring up, it's the same exact 2 vectors. So that's no different than what we did in the last problem. All right? So we had -I plus 3J. So V1 is just the projection of U, V on, or U onto V, V onto U. And we just found that from the last problem, which is -I plus 3J. All right, that was previous. All right, so I cheated a little bit. And then V2, the second one, we just have to find U, take vector U, and we subtract V1. V1 we just found. All right, so in this case, take it. U is 2I plus 4J minus U, the V1 that we just found, negative I plus 3J. All right, so I'm going to have 2 minus a negative 1. So 2 plus 1 is what? 3I. I'm just adding like terms. And then 4 minus 3 is going to be 1. So that here would be my V2 then. V1, V2. The first one is going to be parallel. Second one is going to be orthogonal. All right. The nice part about this here is that the problems you're going to get like in homework or the worksheet, if you come on here, just plug it. Literally just plug it. Just keep replicating. They don't vary much at all. The second one would be orthogonal one. This one here would be orthogonal to this one.
Oh, we already did it.
What?
Is this one already done?
This one was from the first one. That was the projection one we did up above. That's why I put previous. We already did the projection work above. This one here, we just had
What does
to.
that say?
This? Previous. That was the previous problem we just did. So I just copied it down instead of doing it again. All right, and the second one, so that one's parallel to this. This one would be orthogonal to this. All right, last one. Definition of work. I always thought this one was kind of cool. All right, so definition of work. The work W done by force F moving an object from A to B is W equals F times AB. All right, so a child pulls a sled around level ground by exerting a force of 30 pounds on a rope that makes an angle of 35 degrees with the horizontal. How much work is done pulling the sled 200 feet? So I like to draw a little picture. So here's the ground. Here's the sled. Okay? Here's the person. Okay? And here's the rope. All right? So kid's pulling this. He is using 30 pounds. He's putting 30 pounds of force on the rope. All right? And the rope is at a 35-degree angle. Obviously, the fact that he's pulling it up means he's wasting a little bit of energy, right? If he was pulling it straight, he'd be better off, right? We know that. All right. So the question is, how much work is done pulling the sled 200 feet? So, like we just said above, our work is going to be equal to, it's actually going to be the magnitude of that, because the magnitude is the amount of force. Remember, it was the wind yesterday, or the force exerted. Okay, so we need the magnitude of that, and then the magnitude of the direction we're pulling, and then the cosine of the angle. All right, so how much force is being exerted? 30 pounds. All right, how far are we going? 200 feet. That's the magnitude of that direction. And then we want the cosine of what angle? 35. Punch that all into a calculator. It's going to take 4,915 foot-pounds of force. Take that sled 200 feet. Foot-pounds, it's just a unit of measurement for force. It would be, what's that? Yeah. Yeah, foot-pound. It would be like, did you ever hear of grip? Did you ever see grip strength measured?
I haven't seen it measured, but I've heard about it.
You've heard about it? That would be in foot-pounds. So basically, in a foot, how much weight pressure am I putting on that, essentially? All right, so there you go. There will be, listen, there's no homework tonight.